If you have ever touched a doorknob and felt a shock, or rubbed your head on a balloon and seen your hair stand on end, then you know that objects can be charged. This girl's charged because the electrons sort of left her body, and now she's all positively charged. Just remember, it's the electrons, not the protons, that move through objects and jump to other objects because they have little mass. So what do we mean when we say charge? So take this object on the left, it's got some protons and electrons, and this object on the right, we call them Q1 and Q2, charge 1 and charge 2. Q, it's just the symbol for charge. So what can that mean? A charge can be a single electron, a charge can be a single proton. Something that's charged could be an atom or an ion, or a charged object can be a molecule or a group of atoms. It could even mean an entire macroscopic object like a balloon or like the static hairs. Just remember that Q is just a symbol for charge. Q1 could be the doorknob, and Q2 could be your finger that gets shocked. So let's look at these a little bit closer. We have charge 1 on the left, charge 1 on the right. They're a certain distance away from one another, and they'll feel a force of either attraction or repulsion. Let's figure it all out. So we have a little bit more electrons on charge 1, few more protons on charge 2. Charge 1's negative, charge 2 is positive. So the important question here is how much charge? What amount are they positive? What amount are they negative? So if we look at it, Q1 just happens to be negative 3C, and Q2 is positive 2C. What does that mean? A Coulomb is the unit for charge. The Coulomb tells us how charged an object is. And we use the letter C, short for Coulomb, ends with a B. It's a French word. So just remember, folks, that this negative 3 on the left is more charged than this positive 2. Just because it's more negative doesn't mean it's less charged. Negative 3 is a greater magnitude than positive 2. So Coulomb is the unit for charge. Remember that, folks. So here he is. This is Charles Augustine de Coulomb. He, in the 1800s, this weird-looking dude, he investigated how charges behave. And he came up with this law. It looks like this. We have all these symbols here, but we can break it down what they mean. On the left, you have this F. What does it stand for? You guessed it. It's the force. Do they repel? Do the charges repel with a lot of force or a little? By what amount will they attract? Because remember, a force is a push or a pull. They will feel each other. Now, Q1 and Q2, we already know what those are. That's the charge on the object. That's the charge. It's the number of coulombs if you have an imbalance of protons and electrons and you've got a charge. Now, how do they relate? So here, let's start this animation over again. If you increase your charge, you will increase your force. If you make charge number 2 more charged up, it's going to interact with charge number 1, and they're going to feel a stronger force between them. It might be repulsion or attraction, but that relationship, that's a direct relationship. There's a direct relationship between force and charge. The other thing we got to deal with in Coulomb's law is this denominator here. This letter D, it stands for distance. Just how far apart are the charges from each other? Let's take a look at this little animation. If you bring charges close to each other, decrease the distance, bringing these charges close to each other, look at that force. It goes up. It increases. Distance is now increasing here, and the force is going down. So let's see it one more time. Distance decreases, force increases. Distance increases, the charges are further away, force decreases. It's just an inverse relationship, right? Well, not really. That square there, that actually makes a special pattern we call an inverse square relationship. So let's see, how does changing the distance affect the force? How does changing the distance affect the force? Well, let's check it out. If you halve the distance, you make the two charges closer by half, the force, what's going to happen to the force? Do they feel more force when they're closer to each other? Yeah, they do. They feel more force by a factor of 4. They quadruples the force. If the distance is doubled, then the force is actually quartered. Do you see the pattern yet? If the distance is tripled, they're really far apart now, what happens to the force? Oh, it's a really weak force. It's times 1/9. If the distance between the charges is quartered, now they're really close to one another. Oh, that's a lot of force. The force is now multiplied by 16. Now, can you see this pattern? How do we get from this side to this side? What is the inverse square pattern, the inverse square relationship? Well, if you take 1/2 and you inverse it, you get 2/1. You square 2/1. Square means times it by itself. You get times 4. Take 2, inverse it, you get 1/2. Square that, you get 1/4. 3, inverse it, 1/3. Square that, 1/9. This is a pattern here, you guys. 1/4, flip it. Inversing it is like the reciprocal, and then square it, and you get times 16. So that is the inverse square relationship. If you have the distance, you will quadruple the force. The last thing to deal with is this K here. K is just a constant. It's Coulomb's constant. And it's just like little g. We always use 9.8 meters per second squared. It's the acceleration due to gravity. It's a constant. But with K and Coulomb's constant, we always use 9.0 times 10 to the 9th, which is the same as 9 billion. And it never changes, so we don't really have to worry about it too much. But that is Coulomb's law. That's the pattern. I'm glad we broke it down. You got it, folks.